Keep 3 objects separate. The Python builder is a source surface for humans. Calling it constructs a canonical syntax tree. Interpreting that tree later produces a runtime value, such as ranked rows. The source text is not the tree, and the tree is not the result. Building, inspecting, expanding, and evaluating belong to different phases.
But the tree is made of lists. We can print it as JSON and change it with Python. Does that make the query language homoiconic?
It makes the program reified as data in its Python host, which is already powerful. Python can inspect and construct query syntax, but the query language itself has no ordinary quote, list construction, or syntax operations. Code as host data is not automatically object language homoiconicity. Scheme makes the relationship unusually visible. The expression open parenthesis plus 1 2 close parenthesis evaluates to 3. Put quote in front, and evaluation is suppressed. The result is a list whose first element is the symbol plus, followed by 1 and 2. Program representation and a central language data structure have nearly the same shape. That is the recognizable core of Lisp-style homoiconicity. Quasiquote turns that data into a template. Most of the tree remains literal syntax. An explicit unquote marks a hole whose value should be inserted. Bind the whole named term to the syntax tree for 2 times 3, and the template becomes plus, the subtree 2 times 3, and 1. We constructed a new program tree. We did not evaluate the multiplication or the addition. Return to our query language. Recent completed is a convenient surface form with 2 pieces of syntax, a typed cutoff and a source. Its expander produces where, n, and predicate. The completed status test, and the typed date comparison. The macro consumes syntax and returns syntax. In the full program, that output is exactly the canonical type tree we already know. Expansion gets its own phase. First check that the surface macro has the right shape, expand it, then validate and type check the core tree before evaluation. Expansion reads 0 transaction rows. It is not runtime evaluation. And it does not require taking arbitrary text and handing it to eval. A visible phase boundary gives later tools one canonical program to trust. Macros that introduce names can change a program by accident. Here an outer variable named t holds 42. The second argument of or refers to that outer t. A naive or macro also introduces a temporary named t. After textual expansion, the new inner binding captures the reference that used to point outward. The expanded program returns false instead of 42. A hygienic expander tracks syntax identity, not spelling alone. The source binding is t number 0. The macro creates fresh t number 1. Its condition and first result point to number 1, while the inserted alternative still points to number 0. Now evaluation returns 42. Hygiene means that an introduced name does not capture a user's name, and a user's name does not capture the macro's private name. Homoiconicity is used with several nearby definitions, so treat it as a precise design claim, not a badge. In Scheme, the primary program representation closely mirrors lists and symbols that ordinary Scheme code can manipulate, with quotation controlling interpretation. In our query system, the ASD is ordinary Python data, and Python performs the metaprogramming. That is reification plus a host-side syntax API. It is useful without pretending the object language has every Lisp property. The deeper lesson is phase-aware code construction. A macro is a transformation from syntax to syntax, with explicit inputs, an inspectable output, and rules about names. Our first expander used a special branch for one macro. Add normalization, optimization, algebra, and more macros, and branches will spread everywhere. Next, we replace those branches with declarative patterns, bindings, substitutions, and named rewrite rules.